Welcome. This episode's topic is all about magnetic fields, and to understand what a magnetic field is, let's look at an electric field to begin with. Okay, let's start with something very familiar, and we are familiar with electric fields. And the question is, if I told you that there is an electric field, a uniform electric field towards the right, and the electric field is 100 newtons per coulomb, what does this mean? So let's answer this question, and then we'll go to magnetic fields. Well, we know what it means. Electric field is a measure of force per unit charge, right? So this is what electric fields are. It's a measure of force per coulomb. Okay, a coulomb is our standard force per unit coulomb, or force per plus 1 coulomb, a positive coulomb. All right. Okay, so that's what this means, and therefore, if I take an example, if I take a charge of say plus 3 coulomb, then that charge is going to experience a force, and that force would be in this direction, and that force would be, well, let's see, 100 newtons is for 1 coulomb, so for plus 3 coulombs it would be 3 times 100, right? 100, and therefore the force acting on this guy would be equal to just 300 newtons, and hence we say electric field E by definition is the force acting on any charge Q divided by that charge. As you can see over here, if I take 300 and divide by 3, that's where I get that hundreds, right? So to take the force acting on any charge and divide by the charge, and that's where we get this newtons per coulomb. All this is something that you must be familiar with, and if you're not familiar with this, then you should stop this right now, go back and revise your electric fields or whatever. Anyways, now the question is, what is the definition of this thing called as a magnetic field? How do we define a magnetic field? So what we could try and do is we can say, okay, we're going to define magnetic field in the same way how we define our electric field. And so to do that, we need to ask ourselves, just like how in electric fields we have a positive and a negative charge, what do we have in a magnetic field? So let's put this question. Let's look at this question in a little bit detail. So for electric fields, for electricity, we have positive charge and a negative charge, and this guy is the source of electricity, and this guy is the sink of the electricity. So the question is, for magnetism, what do we have? Because I think if we answer this question, maybe we can define our magnetic fields analogously. Well, if you have ever played with magnets, then you know that in every magnet, I mean, who has not played with magnets, right? And you know that every magnet consists of 2 poles, the North Pole and the South Pole. And therefore, I think it's analogous that North Pole acts like the source. I mean, we could choose any one of them, but usually we say North Pole is the source for the magnetic field, and we can say South Pole is the sink for the magnetic field. And hence, just like how we define an electric force as force per positive coulomb, we could now attempt a definition, and we could say magnetic force. This is, by the way, magnetic field. We use the symbol B because we need M for something else. So this is magnetic field, really. Anyways, what we could now say is magnetic force. Magnetic field can be defined as force. This is the force per, just like how we have positive, we're going to use north. Force per North Pole. Oops. All right. So this could be a very good definition. This is a pole, okay? I don't know why it's acting so funny. Anyways, this is a pole. So we could now say, just like how E is equal to F divided by a positive charge, magnetic field B, so let's just change. Magnetic field B would be force F divided by a unit North Pole. Isn't that a good enough definition? I mean, would that work? It looks fine, except for one tiny problem. And the problem is the following. You see, over here, what we could do is, we could take a positive charge, and we could move this guy over here, and we could keep it over here, and then that positive charge would experience a force in this direction, right? And all that is fine, because when it comes to electricity, we can isolate positive charges and negative charges, so we can move these guys apart, no problem. However, there's a very tiny problem over here. We cannot separate magnetic monopoles. I mean, over here, obviously I can. I could just copy this part over here and separate this guy. But it turns out that is not allowed. I mean, if you were to do this, if you were to actually take a magnet apart, if you were to keep it apart, then you know what you're going to end up with? Well, what you're going to end up with is two magnets, and each one would be north and south. Each one would have its own north and south, and therefore you can never separate a magnet. So, into its constituent poles. So you could try. You could keep on. You could try doing that. You can keep on separating it over and over again. Every single time, what you will see now is you will always end up with a north and a south. So there's going to be a north over here, and there's absolutely nothing you can do about it. And since you cannot separate magnetic poles, so let me write that down, that's important, I think. Since we cannot separate this, and this is a very, very big difference between electricity and magnetism, we have a big problem, because we can never keep a north pole over here. This is not allowed. You cannot keep a north pole, and if you cannot keep a north pole, this definition won't work. And so this whole definition fails, and so we are in big trouble now. How do we explain, or how do we define magnetic fields? And how do we do all, what do we do?